Hello and welcome to the cockpit of a Vickers Valiant bomber, which was one of the British nuclear V-bombers. Now this aircraft is extra special because it's the only one left anywhere in the world. It's also interesting because this was the first British aircraft to drop a thermonuclear bomb during testing in the Pacific Ocean back in 1957. And in this video I'm going to take you on a guided tour around this whole aircraft. First we're going to walk around the outside and I'll point out what makes it unique and interesting, and then we're going to climb back into the cockpit and I'll show you a bit more around here as well. I'm Paul Stewart and I make videos about planes. This includes reviews of flights from around the world and detailed tours around interesting aircraft in museums. If you're into these types of videos, then please check out my channel and subscribe. By the end of World War II, the British bomber fleet included Lancasters and Handley Page Halifaxes, while the new Avro Lincoln had just arrived. But it was clear that these were all outdated with the arrival of the jet engine. In fact, Germany already had a jet-powered bomber, the Arado AR-234, flying from 1944. In 1946, and then updated in 1947, the Air Staff announced requirements for a new bomber powered by jets and to drop atomic bombs. It would have a speed of 375 miles an hour, which was around double the propeller-driven Lincoln, and a service ceiling of around 50,000 feet. Multiple companies submitted their competing proposals, and as we know, 3 were chosen. Now it's unusual to order 3 similar aircraft, but you have to remember that the RAF were operating Lincolns, which were just upgraded Lancasters, while the Americans had the revolutionary B-47, which first flew in 1947. Therefore, out of desperation, to ensure that they had something out as fast as possible, they ordered 3 V-jets. The Avro Vulcan and Handley Page Victor were considered to be great options, but were also unique designs. Therefore the third option, the Vickers Valiant, was chosen as a safer and more traditional design. In fact, it was called the quote unfunny design, highlighting its conventional shape. The first one, called the Type 660 registration WB210, first flew on the 18th of May 1951. This was a full 15 months before the Vulcan's first flight. After further testing and the crew training was complete, the first Valiants became operational in July 1955. A month after the first flight, the 660 was renamed the Valiant after a survey of Vickers employees. Up until then, RAF bombers were usually named after cities such as the Canberra, Halifax and Lancaster, but with the new jets, a new naming convention was required. Starting at the nose, and what's obvious is the engineer's appreciation for round shapes, as these were both aerodynamic and best for pressurization, as the forces would spread evenly around the edges rather than focusing on the corners. This seems obvious now, but back then having a circular emergency exit door in the fuselage wasn't necessarily the standard. Here's the cockpit section on display at the Brooklands Museum, and you can see the round pressurized bulkhead at the back. I'll talk about the ejection seats later, but this was initially planned to have an ejection pod where the whole crew compartment would be ejected, similar to what we see on the F-111, although that was too complex and the idea was canned. This here is a plug fairing positioned over the in-flight refueling boom, used when the mission wouldn't require refueling. It was also designed to have a removable tanker system fitted in the weapons bay, including a hose drogue unit and fuel tank, allowing it to operate as an airborne tanker itself. In fact, it went on to become the RAF's first aerial tanker. The system was attached to the same suspension units as the bombs, allowing it to be easily and quickly converted back to a bombing or reconnaissance role. But the negative was that they had to open the bomb bay doors when refueling, which had an adverse effect on the airflow. Later tankers had a system flush with the fuselage rather than simply adding it inside the weapons bay. In the lower part of the massive nose was an advanced NBS, which stands for the Navigation Bombing System. This used a H2S Mark 9A Yellow Aster radar, in addition to a green Saturn Doppler navigation radar and a GH radio location system. The NBS was first used in anger on board one of these Valiants in 1956 to attack the Egyptian Air Force in Cairo during the Suez Crisis, and the final combat use of the system was in the Vulcan during Operation Black Buck in the Falkland War in 1982. This device up here is a floodlight for the refueling probe so a transfer could take place at night. Underneath was a blister which allowed the bombardier to lie prone and pinpoint the target, and we'll have a look in there shortly. They could also take over control of the autopilot and fly the aircraft leading up to the weapon's release. This pipe up here was the refueling pipe. Because the whole nose section was a pressurized compartment, the fuel lines entering and then exiting this to enter the fuel tanks further back would compromise its structural integrity, so instead they ran the pipe along the outside. Moving up, and we have the oval-shaped crew entry door, which had been removed in this example because we'll be climbing up through it shortly. This here was a window for the crew inside the lower compartment, and below that is a warning sign for the ejection seats. But unlike the B-52, for example, there were no downward firing seats, so the 3 crew down here had to physically jump out of this crew door. This was a similar idea to the Vulcan, although easier as there was no nose wheel to avoid hitting like on the Vulcan, or like with the Victor, which had closer air intakes that you'd certainly want to avoid. The 2 pilots upstairs had their own upward firing Martin Baker Mark III ejection seats. Sadly, on January the 11th, 1952, the first prototype was lost during testing due to an onboard fire, and all of the crew managed to escape except for the co-pilot who struck the tail after ejecting. This fin up on top was for the UHF aerials. This object here is a ram air intake to introduce cold atmospheric air to cool the electrical and radar system inside the fuselage. Now, as you know from a hard-working phone or laptop, a lot of heat is generated, so imagine how much heat will be generated by systems 100 times larger. Let's look up at the engine inlets, which were originally rectangular on the first prototype, as you can see here, but were later replaced with these larger double oval designs to improve airflow for the high-powered engines. These here are internal strakes to straighten up the airflow. These were powered by multiple different variants of the Rolls-Royce Avon turbojets. The positioning of the engines within the wing root reduced drag compared with the pod design like what we saw on the B-47. But disadvantages included poorer access for the maintenance crew, and replacing a whole engine was more complex than simply changing the pod. And uncontained engine explosion or fire was now much closer to important structures too. In fact, the de Havilland Comet jetliner had engines in a similar position, and they later added armour plating around those to protect the rest of the wing and fuselage, as well as the other engine, but obviously this increased the weight. I should also say that positioning the engines inboard does result in the wing not requiring as much structural reinforcement, therefore it can be lighter. But then it complicated the design as the wing spar had to move around the engines. They were initially planning to install de Havilland Super Sprite liquid rocket boosters attached under each engine pair. After being expelled during takeoff, these would drop off and float down with a parachute. They were approved for service, but as turbojet technology improved, they realized that these rockets were no longer needed in the production version. For added power, these were fitted with water methanol injection, which provided around 1,000 pounds of thrust per engine for around 45 seconds, and I've explained the mechanism with some photos in my B-47 video. This production version had protruding jet pipes, while the original prototypes had shorter ones. This aircraft in the photo was the one lost to an in-flight engine fire I mentioned earlier, and they realised that fuel had pooled in the jet pipes during in-flight engine shutdowns. So lengthening the pipes, amongst other changes, helped resolve that issue. Looking down at the main landing gear, which was in an unusual tandem layout, retracted into the wing. The tyres themselves are much larger than what we saw in the Vulcan, meaning that this could potentially operate from a less well-developed airport, as the larger tyres could absorb imperfections in the runway and tarmac. This was the reason why the TSR-2 had such large wheels. The tandem layout meant that while these were wide, they were fairly thin, making it easy to fit up into the wing. If they were positioned next to each other, similar to the B-29, they would need a much larger space in the wing or fuselage, which then couldn't be used for fuel, weapons, or other equipment. There were only 2 hydraulic systems on board this aircraft, and they were the brakes and the nose wheel steering. Everything else was electric, as this was lighter and more reliable. In fact, even the hydraulic pumps were electrically driven. Of interest, the updated B2 version I'll mention later was designed for low-level flights, so the wing was strengthened and fuel capacity increased for the less efficient low-level flying. The main landing gear was replaced with 4 wheels and moved further aft and folded up into large fairings called speed pods, and I'll mention that later. I'll mention the weapons load later, but just quickly, this here is a Yellow Sun, which was Britain's first operational high-yield strategic nuclear weapon. Now the name only applies to the outer casing, while the warhead in this Yellow Sun Mark I was known as the Green Grass, and the Yellow Sun Mark II had the US-designed Red Snow warhead inside. Behind here was the nose wheel, and the doors acted as mudguards to stop debris being kicked up and potentially into the engine intakes. This view here highlights just how low to the ground the whole aircraft was. Moving back, and we see this external fuel tank positioned under each wing with a capacity of 7,500 litres or just under 2,000 US gallons. Vickers had installed these as they hoped to enter this in the 1953 London to Christchurch air race, but apparently the Air Ministry vetoed their entry, allowing the English Electric Canberra to win. The tanks went on to be installed in most Valiants anyway. Now they could jettison the fuel inside these if needed, and nitrogen would be used to purge the tank, and in extreme conditions, they actually could drop the whole tank. There were early plans to position bombs here, but that didn't eventuate. In addition to inside the wing, there were the main fuel tanks in the upper part of the fuselage above the weapons bay. Moving further aft, and we have the tailplane with the horizontal control surfaces moved up the vertical fin to clear the jet exhaust. This device here was the ram air intake for the artificial fuel system. The flight controls were electrically boosted, so to stop pilots from inadvertently yanking and pulling too aggressively because they wouldn't be getting any natural feedback from the surface itself, these artificial fuel systems would use pressure generated from this ram intake to give the pilot's control more of a conventional feeling. Now the pilots were trained to fly the aircraft without any electrical boosting, although it would have been quite a workout. The control surfaces back here were otherwise fairly standard, with these trim tabs for minor adjustments on both the horizontal and vertical surface. And inside the tail cone was an ARI 5800 orange putter tail warning radar. Apparently a tail turret similar to what we saw with the B-47 was considered, but that didn't eventuate. In fact, there was no onboard defensive systems. One of these did come across an Egyptian Air Force Meteor, but it was able to outmaneuver it, and I suspect that the Egyptian pilot themselves also wanted to leave the fight as soon as possible. 8 Valiants were modified for a radio countermeasures role, which would now be called Electronic Countermeasures or ECM. These were fitted with AN, APT-16A and an AN ALT-7 jamming transmitters, an airborne cigar and carpet jammers, AN APR-4 and an AN APR-9 signals intercept receivers, and shaft dispensers. Valiant WP-214 was used to test newer ECM equipment that would have been fitted to the other V-jets, as you can see here. I'll mention this aircraft, which is XD-818 and sadly the only intact Valiant left anywhere on planet Earth. It first flew on the 4th of September 1956 and is one of 8 Valiants modified by Vickers for Operation Grapple, which was to test the first hydrogen bomb. In fact, this actual aircraft dropped the first ever British H-bomb codenamed Short Granite on the 15th of May 1957 on Christmas Island. She was converted to a BK-1 tanker in 1961 and repainted in the low-level grey-green camouflage scheme in 1964. But later the same year, she was grounded with the entire fleet after the spar fatigue problems were identified, and I'll mention that later. She was thankfully preserved and put on display at RAF Marham, then transferred to the museum at Hendon before eventually being transferred to Cosford, where she remains inside the Cold War exhibition building next to the other 2 V-jets. Now let's discuss the weapons bay, which was 32 feet long, 6 feet wide and 5 foot 6 inches deep. It could carry a single 10,000 pound or 4,500 kilogram bomb, or 21 1,000 pound conventional bombs, or multiple different nuclear bombs. This here is a WE-177 nuclear bomb introduced in 1966 and carried by the V-jets, the Jaguar Tornado Buccaneer and the Sea Harrier. Their blast yield varied between 0.5 kilotons and 450 kilotons, and for comparison's sake, the Hiroshima atomic bomb was just 15 kilotons, so this could have been monumentally more powerful. This could also be used as a depth charge and dropped by Navy aircraft to take out submarines. It replaced the next bomb, of which this could carry 2 of, the Red Beard, which was Britain's first tactical nuclear weapon. Here's this type detonating in Maralinga in Australia as part of the British Operation Buffalo, where we let you Poms blow some stuff up in our backyard. You'll notice here that the nose wheel has actually been raised, so the fuselage would usually sit lower to the ground, so as we spin back around to the bomb bay, it's worth mentioning that the doors would actually be retracted up into the fuselage during the loading of weapons, rather than opening down like you see here in my footage of the Vulcan now. And the fact that I'm filming while walking underneath the Vulcan just goes to show how much higher it was off the ground than the Valiant. This could also have a reconnaissance role where a removable crate could be installed in the bomb bay with multiple high-resolution cameras angled in various directions, and these would operate through slide-back doors within the bomb bay doors, and you can see those in this photo. There was discussion about underwing pods with photo flash flares, but that didn't make it into production. There was also a tanker roll, and in this diagram here of the bomb bay looking from behind, you can see another fuel tank and the drogue here that would have extended down to the next aircraft. Here's a photo of an actual Vickers with the refueling pod attached. To ease the bomb loading, they used a Simon's bomb hoist, which was mounted on the back of a truck. This would position a column down through the wing, and in this example, and also in the center of the fuselage, and then this would lift the fuel tank in this example, or weapons, or other objects into the bomb bay. This saved the weight and space of having an onboard hoisting equipment, and because it sat so low to the ground, there wasn't room for a standard hoist underneath. Now it does raise a question of why they didn't lengthen the landing gear, but that would have both taken up extra room within the wing so less fuel could be carried, and they wanted to keep the nose as clear as possible for the advancing new bomb and navigation equipment. We'll have a look at the wing, which was difficult to film because of the F-111 underneath it. It was a shoulder-mounted, compound-swept wing with the inner third having a 45-degree angle sweep back, while the outer third had a shallower angle of 24 degrees. This was to provide the best compromise between high-speed and low-speed performance, and while it became a common design, it was revolutionary at the time. The Vulcan, for comparison's sake, initially had a straight leading edge, but a deflection was later added, which helped improve its aerodynamic performance. It had an almost straight trailing edge, featuring electrically operated double-slotted flaps that were scalloped out around the engine exhaust, so improved lift, as opposed to the usual practice of just not extending the flaps past the engine, so this design would still add a small amount of extra lift, and that all adds up. Sweeping around and looking at the wing's trailing edge, and you can see these air brakes which would be extended when the aircraft would dive down from higher altitude to begin the bombing run underneath the enemy radar. These would stop it from overspeeding on the descent. The flaps were electrically operated because, again, electrical cables and motors were lighter than hydraulic fluid lines and less susceptible to damage from shrapnel, which is the same reason why the B-29 Superfortress also used mostly electrical systems. Moving forward, and we see the tail of another V-jet, the Handley Page Victor, although that'll be for another video. Now I'll mention the colour which changed throughout the Valiant's career. Initially, they were silver before being painted white when equipped with the nuclear weapons, with the whole idea being that it would help reflect the nuclear flash. But they left the RAF Randalls on them in solid red, white and blue paint, and it was realised that these might be burned into the aircraft skin by the nuclear blast. Instead, they used these faded colours for both the Roundel and serials, which would otherwise usually be black. This is a black and white photo, but even still you can make out that the Roundel and text was much thicker and brighter on this example before they changed to the faded colours you see here on 818. In 1964, they switched to a green and grey camouflage paint scheme due to the change to low-level flying, so from above they would blend in with the ground. As we walk around to the interior, one more thing. If you enjoy these types of videos, then please consider becoming a channel member. There aren't any perks, but these videos cost quite a lot as I'm travelling from Australia, so I appreciate any help. No worries if the finances are tight, but please give it a thumbs up as that's free and really helps the channel. Let's enter the crew entry door with a quick look at the port side engine air intake to help get your bearings. On this lower level were 3 crew positions sitting facing aft, and you can see the back of those chairs here, which remember were not ejection seats. On the opposite side of the fuselage was the observation window and an emergency exit. This above it was an anti-flash screen made of silicone rubber and glass cloth that would need to be lowered to protect the crew from the atomic flash. When looking up here on the left was the pilot and co-pilot's position. Those of you who have seen my Avro Vulcan video will note that it's a similar layout. It really was an honour being allowed to film inside this incredible piece of history. Taking a step back and down here was the bomb aimer's station. They would lie prone and release the bombs or take photos, and then return to the regular seat during the rest of the flight. There was a sight over the window, as you can see here, and on the starboard side were controls for the bomb release. It would get very cold down here, so heating was added for the photo reconnaissance versions when the crew member could be down here for hours on end. This here was the amenities, and on the left was a ration heater for liquids, and it was perfectly sized for a can of Campbell's soup, and the crew would pierce it with a knife from the rescue dinghy. There were 3 of these and took between 20 and 40 minutes to heat up the soup. This on the right here was the toilet. You would remove the lid and urinate into the tube. This one was for the pilots, and this one was for the rest of the crew. For bigger deposits, that would go into a container full of chemicals that would be sealed up and removed at the destination. This contraption down here was the calculator for the NBS I mentioned earlier. This red cassette on top would provide information about the weapons being carried, and that would all be input into the system that would provide directions towards the target. Once close enough, the target would appear on the radar screen, and the navigator would guide the aircraft towards it. Then once within range, the NBS would take control of opening the bomb doors and release the weapons at the exact correct moment. Optical bombing sights were kept for redundancy, but otherwise these more modern systems worked very well. Moving up, and we see the sextant dome. Now you'll have to remember that radar waves can be detected by the enemy. In fact, the F-117 Nighthawk had no radar for this reason, and check out my video for more information on that. And the B-2 Spirit had a very advanced radar that was specifically designed to avoid being detected. So with the Valiant, the crew would navigate via the stars using the sextant and only use the radar intermittently to ensure that they were on track with the target, and then hopefully minimize the risk of the enemy picking up their radar waves. Looking closely here, and you can see the release button for the onboard inflatable dinghy that was positioned up here and ready to be used in the case of a water landing. Let's have a look at the crew seats lined up along here. On the starboard side and with the window view was the navigator radar with his swiveling chair on tracks, and he was the radar bomb aimer. In front of him was the H2S radar indicator, and this control stick was for the H2S Control 626. This was used to move the center of the image around so that he could see the full radar response. It could also be used to fix the aircraft's position and for selecting a target. The NBS navigation control panel is here. In the middle was the navigator plotter's position, and this guy was also the visual bomb aimer, having to drop down into that dome we just saw below. You'll notice the radiation warning, and that's because they use strips of radioactive luminous material that would identify the emergency exits in low light conditions. Bailing out of a falling plane was hard enough, so having some illumination of the exits would be a big help. The eyepiece here was for the GH indicator, which was another radio navigation system, and the rubber hood was to prevent the reflected light in the cockpit from corrupting the images displayed. And here on the port side is the Air Electronics Officer, or the AEO, who also had another window with the flash shield. In front of them was communication and electrical equipment. As I said before, the only hydraulic systems were the brakes and steering, so this guy managed every other system. This yellow object was to urgently depressurize the cabin that would need to be done before jettisoning the crew entry door prior to abandoning the aircraft. Otherwise, the pressure differential would suck everyone out all at the same time, causing a jam in the door. As I mentioned before, these 3 crew had no ejection seats, so they'd simply have to jump out one by one. It would have been incredibly difficult as the plane hurtled towards the ground, rotating and potentially falling apart. There was always the risk of hitting parts of the aircraft on the way out, so they were instructed to ball up, as you can see in this photo. Sadly, the expectation was that the chance of survival was quite low. I think everyone was surprised when the first prototype crashed, and all 3 lower-level crew members survived the bailout. And, as I mentioned earlier, the only fatality was the pilot whose ejection seat didn't lift him fast enough to avoid the tail. Now turning around and looking forward, we have the 2 pilots positioned, sitting on Martin Baker Mark IIIA upward firing ejection seats. It's hard to convey with the footage here, but it really was cramped up there. And I'm fairly agile, but it was difficult to climb in. I remember reading about the Vulcan, where the roof was so low that the two pilots would sit with their head slightly angled away from the fuselage, so you could pick a pilot from the co-pilot because they'd have a permanent kink in the neck, angling away from the roof, but in opposite directions. Well, that was the story. Here's the hand wheel in front of the pilot, and it's an interesting design because instead of being connected down towards the floor, the column is off to the side, freeing up space for the legs underneath. Here on the left was a window that could be opened, and it gives you an idea of how thick the glass was. Now it's all analog with no screens anywhere, with basic dials in front of the pilot, and engine parameters such as the exhaust temperature, RPM and oil pressure lined up in columns for each of the four engines. Up here and in the centre, you have the engine fire extinguisher systems. Here's the four throttles, and below that are a whole range of controls, including for the trimming, and further down was the autopilot controller. Over on the co-pilot's position, many of the same dials. You can see the Mach meter here, and it had a top speed of 567 miles an hour, or 211 kilometers an hour at 30,000 feet. Here's a linkage for the yoke, and many buttons for things like the lighting, in-air refueling, and fuel movement between the tanks to maintain the center of gravity. This here is the co-pilot's urine tube. Here's the dials for the nose wheel steering and brake pressure, which were the only hydraulic systems on the plane, as I mentioned before. Moving back around forward, and you've again got this white flash shield that would be rolled down prior, well, hopefully, to a nuclear explosion and flash, and this would cover all of the windows on the aircraft. These here are the controls for the cabin pressurization system. Heated and pressurized air is bled from the engines, and then air conditioned, so made a tolerable heat and pressure before entering the cabin. No pressurization is needed up to 9,000 feet, but above that and up to 47,250 feet, the pressure equivalent of 9,000 is kept. But when in a combat zone, it remains unpressurized up to 25,000 feet and then kept at that level at higher altitudes. Now the idea was that if you were hit by a stray bullet or shrapnel and the fuselage was compromised, you would not want a large and sudden pressure differential that could potentially tear the hole much bigger. Obviously though, supplemental oxygen would be needed by the crew. Spinning around, and apologies for my subpar footage here, is the jettisonable cockpit roof, and you can see the hood detonation safety switch here because this will explode off just prior to the ejection seats. And below that, we can look down at the three crew positions that we just looked at earlier. Production stopped in 1957, and in total 107 were built, including the three prototypes. The B1 was the pure bomber type, and there were 37 of those, including the aircraft in this video. 11 Type 710 bomber and photo recon variants were built, 14 Type 733 bomber and photo recon and tankers were built, and 40 Type 758 bomber and tanker versions were built. There were two more worth mentioning. There was the B2, and unfortunately only one was ever made. It was planned to act as a pathfinder aircraft that would fly at low level to identify the target and drop markers such as flares and smaller bombs that the main high altitude bombing force could spot from a distance. This was a World War II idea. It would need to tolerate the highest strains flying at low level, so it had a strengthened airframe and wing. Instead of the landing gear folding up into the wing, they changed it to fold backwards, up into new fairings called speed pods, so the wing structure could remain uninterrupted and stronger. And there was also more room for internal fuel storage. But because of the extra weight further aft, the nose was extended forward to maintain the centre of gravity, and this allowed for more room for equipment. It was also faster, and planned to have a more powerful Rolls-Royce Conway turbojets, although the prototype had Avons. The B2 first flew on the 4th of September 1953 and was painted in gloss black. It performed well, and initially 17 were ordered by the Air Ministry, but the program was eventually cancelled as the Pathfinder concept was rendered obsolete as weapon targeting systems improved. The Valiant was also used for in-flight testing. WP-199 was used as an engine testbed for the P-1127 program, which led to the Harrier. Here's a Pegasus engine with the rotating exhausts mounted in the bomb bay. Even though it wasn't planned to carry it in combat, the Valiant was also used during the Blue Steel standoff nuclear missile development. It test dropped a 2/5 scale rocket-powered model that was used for aerodynamic testing. And finally, and also a very interesting variant, was the Type 1000, which was to have a low-mounted wing and be a large air transporter. This could have been used by both the military and sold to civilian airlines. There was a prototype being assembled, but the program was cancelled prior to completion, and then it was scrapped. With the improved Soviet defensive systems, the plan for higher altitude bombing runs changed to low altitude attacks, where they would fly underneath the radars. This is when the paint was changed to the ground camouflage design I mentioned before. On the 6th of August 1964, WP-217 was on a training mission when they all felt what sounded like a large impact. They landed and were horrified to discover the wing spar fractured and the wing was noticeably drooping. Vickers and the RAF had actually already begun inspecting their spars after fractures were found on the Viscount airliner, which used the same alloy. Major stress fractures were found on almost every Valiant, so low-level operations were immediately ceased. Ironically enough, the B-2 Pathfinder version I just mentioned would have been far better as a low-altitude bomber because of the reinforced wings, but that program was already cancelled. Repairs were considered, but the Defense Department decided it was not worth the cost now that the Vulcans and Victors were flying, so the entire fleet of Valiants was grounded on the 26th of January 1965. This aircraft we explored today performed the last Valiant bomber sortie ever. The RAF found themselves without a tanker, so the Victor tankers were rushed into service. Most Valiants were scrapped where they were grounded and became target practice or used as firefighting trainers. Some were kept flying and used for testing, as I mentioned earlier, and this aircraft XD-818 was preserved. If you enjoyed the video, please give it a thumbs up so that YouTube will show you more similar videos. I have many more similar airplane tours on my channel and many more coming, so please check those out. Thanks for watching.